So we have seen how a neuron is modeled. From now on, we will call neuron such a model. These neurons are the essential elements of neural networks. We now detail the first method that aggregates neurons and allows us to train their parameters, weights and biases given a training set. This method is called the perceptron. In the late 50s, Frank Rosenblatt, a psychologist at Cornell, worked on decision systems present in the eye of a fly, which determine its flee response. Later on, in 1958, he proposed the perceptron algorithm, calling it Mark I perceptron. This system is based on the neuron developed by McCulloch and Pitts. More precisely, here is a representation of the perceptron model. You see on the left an input retina, which is nothing but the retina of the fly. Some pixels of this retina, which can be seen as the first layer of the perceptron structure, are connected to some association units, which compose the second layer of the perceptron. Finally, the association units are connected to some output units, which compose the last layer or output layer of the perceptron. So, all in all, the perceptron is composed of 3 layers. There are connections between each consecutive layer. However, there is a major difference between the connections. The connections between the input retina and the association units are not modifiable, they are fixed once and for all, and the weights associated to these connections are also fixed. Hence, it's not possible to train these connections and to modify them according to some data-driven algorithm. By default, each association unit takes as input 6 nearby pixels of the input retina and computes the weighted sum of these values. This sum is the output of the association unit, which serves as the input of the output unit. Each unit in this architecture corresponds to a neuron of McCulloch and Pitts. Therefore, each output unit of the perceptron produces either 0 or 1. The perceptron was first implemented in 1958. You can see a picture of this machine here. This big machine is only able to process an image which is composed of 400 pixels, equivalent to the retina of the fly. In this machine, the connections between units are created thanks to wires and the weights are adjusted via potentiometers. So, in this machine, you can tune manually the weights and biases of the perceptron. Needless to say that nowadays we are able to run perceptrons which are much smaller than this machine. It turns out that all computers are able to build models much more complex than a single perceptron. But before moving towards more complex models, let us focus a little bit on the perceptron. The most simple perceptron model is composed of a single output unit. Since the first weight between the first and second layer cannot be optimized, we can consider them fixed. In that case, the perceptron algorithm amounts to the model here, which is nothing but a neuron. As for the McCulloch and Pitts neuron, the inputs are aggregated, a bias is added, and an activation function is applied to this sum. Here, the activation function is simply the indicator function. So the perceptron model is nothing but a neuron model. One small difference being that the perceptron can take continuous values, x1, xd, as inputs, whereas the McCulloch and Pitts neuron can take only binary values as inputs. A major contribution of Rosenblatt is to produce a perceptron algorithm which allows us to tune automatically the weights and biases of the perceptron. Indeed, note that here we would like to set these parameters depending on the data we have at our disposal. This is the learning phase that we see in the next slides. Now assume that we have at our disposal a dataset Dn of pairs xi, yi, where the labels yi belong to -1, 1. To simplify the notation, we set W tilde to W1, WD, B. In that way, the value tilde stands for all parameters in the perceptron. Similarly, we set xi tilde equal to xi1. Note that xi tilde is the input modified to take into account a constant component which corresponds to the bias. The perceptron algorithm, which aims at finding a set of optimal parameters, weights and bias, works as follows. We start with W tilde equal to 0. Then we're going to repeat the same operation over all samples. If yi times W tilde xi tilde is smaller than 0, then we modify W tilde into W tilde plus yi xi tilde. Otherwise, we do nothing. Why do we look at yi W tilde xi tilde? In order to know if we need to modify the weights. The prediction given by the perceptron is equal to 1 if W tilde xi tilde is larger than 0. Let us imagine that yi is equal to -1. So if yi w tilde xi tilde is negative, then it means that w tilde xi tilde is positive, which in turn means that the perceptron is going to predict 1. In this case, the prediction is 1, but the true value is -1, so the prediction is incorrect. We can show the same thing if we assume yi equal 1. Therefore, yi times w tilde xi tilde negative is equivalent to an incorrect prediction. So we want to modify the weights and the bias of the perceptron if we find an example which is incorrectly classified, which is equivalent to yi w tilde xi tilde negative. Why then do we modify the parameters in that way by letting w tilde equal w tilde plus yi xi tilde? If we find a sample xi tilde such that yi w tilde xi tilde is negative, and if we replace w tilde by the given value, the updated quantity yi w tilde xi tilde is equal to the previous one plus the square norm of xi tilde. This update has increased the quantity which was negative. If the new quantity is positive, then it means that the sample is correctly classified. If not, the quantity is less negative, and we can hope that several passes on this data will lead to a positive quantity, i.e. a sample which is correctly classified. In general, when we want to optimize parameters in a machine learning algorithm, we use gradient descent, or some closely related iterative procedures. To do so, you need to define a loss, and the procedure works as described below. Can you think of a loss which would make the previous perceptron algorithm appearing as a gradient-based procedure?